All right, here we go. So in chapter 6, we're going to talk about normal distribution. This is where a lot of your statistics come from. This is your bell curve. This is where I'm like heavy hard on 6, 7, 8, and 10. When you applying statistics in the career field, everything else before you saw was kind of stuff that you should have seen throughout your grade school, probability, things like that. Um, but this is more of what you'll see, what statisticians actually use on a regular basis. We'll definitely be doing the equations. I'll show you things to use for the calculator. Um, Statisticians normally just use a computer program and just type in all the data, and they just know how to read the data. So once you calculate the data, you're gonna have to know how to read it. And that's basically what chapter 6 prepares you for. And then chapter 7, 8, and 10 are all the different types of distributions other than just normal. All right. So that's kind of a gist of what we're about to get into to wrap up this semester. And believe it or not, we are really close to being done with this semester. All right. Okay, there we go. All right, so random variables can be either discrete or continuous. Oh, writing. Discrete or continuous. Continuous variables such as heights of adults, body temperatures of rats can assume all values between any two given values. Remember, continuous is like your decimals, discrete is like your counting numbers. Um, Although no variable fits a normal distribution perfectly, the normal distribution can be used to describe many variables since the deviation from a normal distribution are smaller. A normal distribution basically means everything is pretty much in the middle and then it kind of tapers off throughout the process. All right. So let's get into 6.1 today. 6.1 again is normal distributions. Our first objective is to identify the properties of a normal distribution. So let's talk about definitions first. So if a random variable has a probability distribution whose graph is continuous or also known as bell shaped, so just so you know, this is normal. Pretend that's a bell, like a perfectly symmetrical bell. And symmetric, it is called the normal distribution. The graph is called a new normal distribution curve. Right. And then we get into these equations for normal distribution. So we can calculate like our y values by simply taking, well, I say simply, but this is an e, which represents the empirical number of 2.7 some blah, 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 blah. I don't know the rest of it. Raised to the negative of whatever your x is minus the mu, or your sample basically, squared divided by 2 times the variance, all divided by the standard deviation times the square root of 2 pi. Again, oh, there's is E again is 2.718. Pi can be estimated as 3.14. Recall that mu is the population mean and the lowercase sigma is the population standard deviation. But do realize if it has a square, that represents your variance. Now, if you don't know your variance, you don't have to go calculate it. Just square your standard deviation. You got the variance. That's basically what it's stating here. Oh. All right, so the shape and position of the normal distribution curve depends on the parameters for your population mean and your population standard deviation. Now this graph is about to give you what I'm about to say, but I figured I could put my spin on this to make it a little bit easier for you to understand. But if this is a normal bell curve, and I think I've talked about this before, this right here, the center here, that represents your mean population. And then if I go about right here, this would represent one standard deviation away, and this is -1, but still one standard deviation away just on the left side. And then we talked about from here to here is about, was it like 68%? It's not going to talk about it, but this is like 68% of your data. And then we talked about this being a second standard deviation. And from here to here, sorry for the freshmen, they're outside doing things. It's about 95.4%. And then at 3 standard deviations, we can roughly say this is about 99.97% of your data. Anything outside of that is most likely going to be considered an outlier. Now, these are just rough estimates. All of your data could technically be in 2 standard deviations. This is just roughly of anything that tells us it's a normal distribution. We can pretty much predict this right here. All right, so that's my overall on normal distribution. They do supply you some nice clean graphs for you. There we go. Where again, you have a normal distribution. It can be a little plateaued. It can be peaked, more like a mountain cliff than the hill. But it's all still about the same concept, where right here is still 1 standard deviation. A little bit further out will be 2 standard deviations, and further out will be 3 standard deviations, and so on and so on. So again, you can see that even if the mean has changed, the curve still looks the same. It just gets shifted over on a number line depending on what the mean is for that situation. Like if this is 0, this is where it'll be. If this mean is 2, it's still over here. So then your standard deviations would be off that mean. Does that make sense on what this graph is trying to tell you? Yeah, so that the mean can shift the graph left and right. The standard deviation is just going to always be the same amount. The bell curve is still about the same. We good with this? All right. Let's put this into practice. Makes more sense when we do that. So when the population means are the same, but the population standard deviations are different, the curve with the larger population standard deviation is more spread out. So it's what it looks like. It looks like it's an anthill that's been mowed over. So it's a little bit less slopey. Yes, slopey is a word. All right, so it's a little bit more spread out. When the population standard deviations are the same, but the means are different, the curves have the same shape, which you saw on the second graph. But the center of different points along the x-axis. Okay, so again, if the population standard deviation are about, if the means are the same, but the population deviations are different, the one that's a little bit more spread out, or a larger population be more spread out. If you only have 6 people, that's when you're going to get more of a peak because you don't have much data. If we have 150 people, it's more spread out, so you'll have a less of a steep of a normal distribution curve. To build it, though, it's still the same calculation, so don't get tricked up too much on that one. And when it comes to graphing normal distributions, literally just draw the exact same graph every time, and then just graph your mean and your standard deviations amount, and then that's pretty much it. So there ain't too much graphing wise that you have to know of. All right, so let's put a summary to this real quick of what we've seen so far. And this is just theoretical. So these are things that should happen, but it doesn't always mean it's going to happen. So a normal distribution curve is bell shaped. We've seen that now. The mean, median, and mode are located at the center of distribution. So basically that means that we can use the mean, but we could also use the median and the mode as well to calculate our normal distribution curve if we desire that to be what we're trying to express in our data. Remember, statistics is very wonky in a situation that we can skew our data to be whatever it is that we're trying to prove, right? So a normal distribution curve has exactly one mode. So this will not be a no mode or a multi-mode or anything like that. It'll just have one because it's just a one bell curve, it's one curve, unimodal basically. So then the normal distribution curve is symmetric about the mean. The median and mode can be there as well. It just might be not exactly in the center, and we'll see. So, and then what it does, it takes that normal distribution. Just to get it, I'm getting ahead of myself. But the mean's always in the middle. So you could have something like this, where this is the mean. Pretend this is a mu. But if I wanted to do the median, it'd be a little less. Let's say the median is over here now. It's still a bell curve. It's just not as symmetric as it would be for the mean. Same concept with the mode as well. The mode could be like this, where this is now the mode and it's not quite centered. Again, pretend that these are curvy. So mean's always going to be the center, but these guys can be skewed. A lot of times too, some statisticians will have it like this and then also express that this is the median and that this might be the mode over here, but still have it distributed normally around the mean. So just if you see that, it's just giving you more information on the same chart. So the normal distribution curve is continuous. So it will contain all decimals and every value in between. Again, it's just expressing that the data is in between the percentage wise between these two things. Having no gaps or holes for all values of the independent variable, meaning this little line here is a continuous line. We're not having holes or gaps or piecewise functions. The curve approaches, but does not meet the x-axis. It gets increasingly closer and closer while never touching the x-axis. And what that basically means is, yeah, the approaches stuff. We did this a lot in pre-cal. So like for instance, it'll get really close to this line, but it'll never actually hit that line. And that's kind of going back to my drawing above. That's why we say about 99.97% of the data will fall there. There is that 3% or 0.03% that's gonna we might still miss, but we're approaching it. We're not gonna actually hit it. We'll eventually hit it. No, so we'll never hit it. We just might eventually catch all of our data. That might be in this situation. Go ahead. Yes, it just won't go. It won't hit zero or negative for that information. Yeah. All right, and then the total area under the normal distribution curve is equal to, I guess I was off just a little bit, but 99.7%. So again, that 0.3% that it won't actually touch is not going to be accounted for. And most likely that data that's not accounted for is probably going to be your outliers anyways. So it's going to pull your data. So it's you might as well just take it out. Just so you also know, they have a definition for this to add in, but this is also known as the empirical rule. And again, empirical or theoretical is just things that should happen. It might not necessarily mean that it is going to happen that way. It just means mathematically, we've seen this happen so many times that we can pretty much predict this. Oh, I got that's my bad. I got off on my task here. This right here is supposed to just be one. The 99.7 is a different thing. No, that last thing will be the empirical rule. The 99.7. My bad. So this will all add up to your what eventually. Because even though we go to usually 3 standard deviations, we can catch all of it eventually over time. All right. And there's the breakdown there. So the area under the curve, or under the part of the normal distribution that lies within 1 standard deviation, this is what I was trying to write earlier as well, of the mean is approximately going to be 68%. Within 2 standard deviations of the mean is going to be approximately 95%. And then within 3 standard deviations away, it's going to be approximately 99.7%. And this is your empirical rule. So again, things that should happen, but doesn't mean it's gonna happen that way. Not everything is a perfect normal distribution. So you can see here that here's my mean. So this right here should be roughly 68%. Now they went real extra there. But if this was just 68, that means 34% of my data should be on the left, 34% of my data should be on the right. And then if I go 2 standard deviations, then this in total, what's half of 95? 47.5. So this right here would be about 47.5%. This would be about 47.5%. And then if we go even further to 3 standard deviations, this is pretty much going to be, I don't know what, 59.3-ish or something like that. 35 on this side, and the 54, 55, 59 point, right, no, what, half of that's 49. That's it, 49.3-ish, and then this will be 49.3-ish, and then the 0.03 on the outside there. But that just know that when this is the mean and we say this 68% of the data, it's half and half on each side. That's what makes it total. So when we talked about this a little bit when we talk about percentile, when we try to calculate this, we're like, oh, that's 68% of the data. But if it falls right here, it's 68 plus this. So you would have to calculate this on top of the 68 when you're looking for percentile. We'll get over those kind of questions here in a second, though. Any questions on how it's ran? And right below that, they give you the approximates. So there's your 68, 95, and 99.7. All right, so that is what normal distributions look like. So let's look at let's look at identifying distributions as symmetric or skewed. So the normal distribution is symmetric about the mean. The mean. That is, the data is evenly distributed about the mean. When the majority of the data values fall either to the left or the right of the mean, the distribution is skewed. So again, if more data falls on the left or the right, it's being pulled in some direction. When the majority of the data is to the right of the mean, the distribution is negatively skewed. Or left skewed. So if you have more data on the right, again, so we're aware, looks like this. That's a negative skewed or skewed to the left. The mean is less than or to the left of the median. When the majority of the data is to the left of the mean, the distribution is positively skewed. Or right skewed. So again, that would look more like better this way. Something like that, where it's more to the left there. The mean is greater than or to the right of the median. Means just the middle number. The tail of the curve indicates the direction of the skewness. So positive and left is negative, or right is positive, left is negative. So if I have a tail on the left, then we know it's going to be negative. If I have a tail on the right, then I know it's going to be positive. And we've seen this in chapter 1. I think we saw it again in chapter 3 or 4. So this just kind of keeps coming back and forth. And then, of course, they give you some figures, probably better than what mine look like. Right there. So again, you can see a negatively skewed, it's pulled a little to the left. Positively skewed is going to be, not bad, pulled to the right. Positive skew is going to be pulled to the left. And then a normal looks just like this. Right. So you can see like here's the mean, but then the median mode is on the left side of it. Here's the mean, and then now the median mode's on the right side. And then for a perfect normal distribution, the mean, median, mode will all fall in the same category. Does that make sense? So I was trying to show earlier, but they got better drawings than I do. All right, let's look at objective 3 then. So now we're going to find the area under the curve, under the standard normal distribution, given some various z values. This will be important too on your textbook, knowing your z-score so you can calculate what the distribution is. And when we get to that point, I'll show you what you can do to actually use your textbook. All right, so the standard normal distribution is a normal. That just seems like a double there. So a standard normal distribution is a normal distribution with a mean of 0 and a standard deviation of 1. Oh, that's not a 1. That's a 1. Right. So in a perfect ideal world, the mean is 0, and then literally you're 1 standard deviation away on both sides. So 1 standard deviation from 0 is 1, 2 standard deviations from 0 would be 2, 3 standard deviations from 0 would be 3, and then you have the same effect on the positive and negative side. All right, so that's a perfect world normal distribution, ideally. Does that make sense? All right, and then here again is the formula of calculating the standard normal distribution. Again, this is a formula we'll use. To be honest with you, I'm not very familiar with that formula. I feel like we did it a different way back in my day. This looks more familiar to me. All right, so all normally distributed variables can be transformed into the standard normally I can learn how to spell. Great. Distributed variables. By using this formula for the standard score. So again, we've seen some of this before when calculating the percentage wise using what's this guy's name? Chebeck's theorem or something? Schneebeck, whatever his name is. This is kind of what we use to try to calculate. What was it? Jimmy? Yeah. But this is kind of what we use to calculate to help us find that K and then use that then in his formula. So he used K, it's technically the Z score. But basically what you do is you take whatever your sample value is minus the mean divided by the standard deviation. That will give you a Z score. The Z score then will tell us exactly where it falls on a normal distribution curve to tell us what percentile or what area under that curve it takes, how much percentage of it is. All right, so a standard score or Z score is the number of standard deviations that a particular X value is from the mean. And so here is what you're going to have to look up. Table E in Appendix A gives you the area to 4 decimal places under the standard normal curve for Z values from negative 3.49 to 3.49. What that basically means is If it's less than 3.5 standard deviations on the left and the right, the book will give you the answer. So how about we do this real quick? Let's go grab our textbooks if we haven't already, and go ahead and find Table E and Appendix A in the back of your book. I'm thinking so. Oh, definitely not. I'm thinking, yes, we're going to use it. What I'll probably do, Rivers, is I'll probably print out like a copy for y'all to be able to use on the test, so you're not just flipping through the textbook going, I can't find the appendix, and you're like in chapter 6 trying to look up a definition or something. You know, those little tricky ways. Yes, that's very important. So if you pay attention to it, and let's see if I can pull it up real quick. Oh, very nice. It's like a little thing you can take out normally. Does it have all the formulas on it? I'm contemplating and allowing you to use just that on the test coming up. So it has the Appendix A and all the formulas. That's what I'm thinking. Because it's gonna be hard enough for you to do the math, much less memorize which formula to use the math. So I'd rather you, because in the real world, in statistics, you're given the formulas. You just gotta be able to apply it and analyze it. So that's kind of what I'm leaning towards. So I tell you what, that's gonna be a guaranteed. So when you're doing your homework, practice using this chart so you can easily find your formulas and what you're. They do? Yeah, that's what I'm doing. What is it still doing this? Hold on. I got too many. I'm thinking so. Why not? Any objections to it? To use this on the final? Then you don't have to use it. I'll make it optional. What? Oh no, eventually I'll get into the right Alex. It's gotta be this one. It's the only one I haven't tried. That does not look like me. Online appendix. Which one was it? A? Oh, there it is. Appendix A. Appendix A. Table E. Take me there. All right. Perfect. All right. So this is how this works, just to give you a rough idea behind it. You will calculate your z-score using that formula where it's the sample minus the mean divided by the standard deviation. What you're trying to figure out is, all right, how many standard deviations is this X value from the mean? Once you calculate whatever the score is, just so you're aware on how this works, let's say I calculate a negative 2.35. You'll go to negative 2.3 right here, and then travel to 0.5 right there. So the area of that mean would be 0.0094. Now let's think about that. The area under the curve had to be what again? Once I corrected my mistake? 1, right? So if you are negative standard deviations away, are you on the left or the right? The left. So my percent should definitely be less than 0.5, right? Because that'd be 50% of my data, right? And then if you are almost 2.35, so you're roughly like, I don't know, between 2 and 3 standard deviations away, then if we go back to that bell curve right here, like right there, it says about 2.15% ish, right there between 2 and 4. So therefore, I should roughly, and then you also have that 13.59% that's going to be in between that. But that's basically stating right there, if I'm negative 2.35, I am 0.94% all the way there. So here's 2.15% of my data. I'm kind of getting kind of close to that negative 3. It makes sense that 0.94% should be my area under the curve. And on the flip side of that, if I was to look at, I don't know, let's say I calculated a 1.65 or something like that. So what was it? 0, 1, 2, 3, 4, 5 right here. That's stating now I'm about closer over here. So that should be about 95% of my data from here down. Does that make sense on how this chart has worked? So if it's negative, it depending if you're, it's all dependent on what z score you get. If you get a negative z score, that means you're a negative standard deviation, so you're on the left side of your mean. So no, you don't. Oh, well, yes, but your z score can be positive or negative, yes. But yes, the area always has to be positive. It has to be between 0 and 1. It'll never be 0, it'll never be 1, but it'll be between those two. Go ahead. Oh yeah, it'll be that value, and to the left of it is your area. Oh, you don't have to stretch anything. The number you get is already calculating everything to the left. Well, I don't know what the assignment's stating, but if you get a z score of 2, that when you get it here, it's going to be that data calculated all the way there. I don't know exactly what the question's asking you, but it could ask you, like if you are specifically um, 2 standard deviations from the mean, what's that data? So you could calculate what that is and then subtract it from what's not in it to get this total. But we also have it memorized as well. What might affect more is maybe if it has like 1.5% on both sides. The only time you're ever going to have to subtract is if you are calculating a range of your z score. But if you're calculating a single z score, it's going to be that value, everything to the left. Go ahead. Okay, so now it's getting more specific. If it's asking the area of the curve to the right of that data, then yes, then you would take what you get and subtract it from 1, because what this table is going to give you is all this data. But if you specifically want the right, then you're going to have to subtract it from 1 to figure out what's left. Then what you get here is the answer. What do you mean? It counts it as the equal to part. So you don't have to, when I get a z score of 2, or if I get a z score of 1.55, 1, 2, 3, 4, or wait, 0, 1, 2, 3, 4, 5. So that gives me a 0.9394. That is including 1.55 and everything to the left. So that is your less than or equal to, huh? No. That's your answer. 0.9394. It is including. What do you mean? So it's just a less than? I don't know. I don't think it's going to matter, to be honest with you. If it's a less than or equal to, I don't think it's going to matter. I think it would still be the same result. Because you're basically what you're doing is if you think about area of a curve, it doesn't really matter if it's a dotted or a solid line. If you think of inequalities, it's going to still be the same area. So I don't think it's going to matter if it's less than or equal to. Does that make sense? Let's keep analyzing and see what they tell us, because I'm pretty sure that's the case. I don't think it's going to matter. Now, if it's a greater than or greater than or equal to, that's when you're going to want to subtract by 1. All right, so let's jump right back into it. So yes, that's what we'll do for the rest of the semester. I think that's fair, just because the formulas are getting more and more complicated. All right, here we go. So finding the area under the standard normal distribution curve. We'll draw the normal distribution curve and shade the area under consideration. Choose the appropriate type of problem and either use table E in Appendix A or use technology. I think Appendix A is going to be a lot easier because it has our data there, and then go from there. So this one here says find the area under the standard normal distribution curve to the left of a Z value. Find the Z value in table E and use the area given. All right. So if you're asked to find, this is what we were just talking about, Olivia. If you're asked to find something to the left, then all you got to do is just go calculate what this is. So let's do our table now, and let's go find 1.32. So you look for 1.3, and this is 0, 1, 2, so 0.9066. Did everyone easily calculate what that is? Well, it's a calculation that's already been done for you. Go ahead. Are you confused, or he's just picking on you? Okay. All right, so again, that was just 0.9066. All right, let's see. This next one says the area under the standard normal distribution curve to the right of a Z value. You're going to find that value and then subtract it from 1. So we'll do, because again, we're looking on the right, so we'll do 1 minus what is negative 0.67. Perfect. 0.2514. So then all you gotta do now is subtract those two. And what do you get? Yeah. Perfect. Look, it's so close to my hand. Where is it? Is it going off the table? Ah, there we go. Got it. Well, Rivers was over there going, he ain't getting closer to it. And I was like, okay, he must be getting off the table. All right, so let's look at another example. All right, so this one says the area under a curve, standard normal distribution curve between two Z values. We're going to find both Z values and subtract the corresponding area. So here we go. So we need to find out what 1.45 is. So again, what we'll do is we'll come to our chart. We'll go to, I don't forgot it now. We'll go to 1.4. So locate 1.4. And then we need to then calculate 0.05. So that's 0, 1, 2, 3, 4, 5. You would get 0.9265. Perfect. Then you'll subtract the two, yes. So what was it again? 0.9265. This is going to be a larger area because it's further away from the mean. So I'm going to go ahead and do subtracting on this side. And what is the z-score at, what's the area at 2.32? 0.9898. So then you'll subtract those two. And basically what you're doing is, to give you an idea, Here's 1 standard deviation. Here's 2 standard deviations. Here's 3 standard deviations. You're approximately, this is a horrible graph, but you're basically calculating this area right here by subtracting those two numbers. So what do you get here? Right. Any questions on that? So if you're asked for the area to the left, you just got to write the answer down and you're done. If it's asking for the right, you subtract 1. If you're finding the area between 2, you take subtract the bigger number from the smaller number to calculate what that missing area here is. Like over here, when I'm looking on the right side of this guy, here's -1 standard deviation. Here's the mean right here. I basically had to calculate approximately this to get that answer. And when I was looking to the left of that z-score there, here's 1, here's 2. I was basically calculating all of this. That's why I was able just to write that number down. Does that make sense? All right. So the following examples, again, use the technology E or table E or technology. We'll use table E. So in example 1 here, we'll find the areas between 2 given values. So find the area under a standard normal distribution curve between 0 and -3.72. So, sorry, -0.3. What did I say? I don't know. 7 sounded like a good number. So, so what you need to do is calculate a standard deviation of 0. What will a standard deviation of 0 be? And does it need to be on? It'll be 0.5. Very good. I'm curious to see, is it on the chart? It is. And that makes sense, right? Because the mean is literally half of the data. So if you have 0 standard deviations, that means you're on the mean itself. Yes, that one with the E and the square root of 2 pi and all that stuff. No, we're not. That's why when I was looking at that formula, I was like, that doesn't ring a bell at all. I've always just used a table. All right, so what was the z-score of 0? That was 0.5. What's the z-score of -0.32, not 72? 34? 934? 0. Yes, negative. Hold on. Let's go look for it. All right. There's, oh, I gotta go to negative. Yep. So -3012 should be 0.3745. I done forgot it again. What was it? All right, and then we subtract those two. What? I can't use my brain, I'm telling you. What is that's what it feels like. I feel like there's just so much pressure right here. Well, it's not draining. That's the issue, I think. What's the value y'all got? Maybe. Even though I got affected Monday evening. What's the value? What's the answer here? Not 0.6. You're subtracting the 2. Should be, yeah, closer to 0.2, but I don't think it's 0.2 either. 0.1. Close. 255. Yep. Well, so yeah, you're trying to find the area between 0 and -3 or -0.32. I don't know why I keep wanting to say 7. All right, do the next one. Oh, we're looking to the right. So if we're looking, I don't know, maybe. Probably it's what my brain's trying to do. To the right of this one, what would I have to do to look for the right of something? Subtract it from 1. What's the the area at 1.23? And when you subtract those two, what do you get? Go ahead. What's the question? Zero nine three. You had the right numbers, is in the wrong order. You're so close. Did you figure it out? If I have to find something to the left, do I have to do anything? Then that's it. And then you just write it down. We'll continue this discussion tomorrow. Hopefully, I'll have a little bit more energy to move around. And then we'll do 6-2 applications of this.